first speaker is Dr. Walter A. Laviña. He is an associate professor at the University of the Philippines, Baños. He graduated from the University of the Philippines, Baños, with bachelor's degree in biology and master's degree in microbiology. He received his PhD degree from the Department of Biotechnology, Osaka University, where he specialized in yeast genetics. Before coming back to UPLB, he was a researcher at Osaka University, focusing on application of metabolomics in metabolomic engineering of microorganisms. He returned to the Philippines in 2015 as a DOST scientist to establish research program in natural products drug discovery at the University of San Agustin. And for the good of Philippine science, she stayed for good.
So, thank you very much, Dr. Emilio, for that very kind introduction. And thank you to Steve for inviting me. Okay, so this will be the outline of my talk for today. So I guess everybody will be in agreement to say that global warming is one of the most important problems or concerns in the world. So unless you're Donald Trump. So emission of greenhouse gases by humans such as carbon dioxide, nitrous oxide, or methane actually increase the global temperatures by about 1 degree Celsius since environmental times. Okay, so scientists attribute global warming to the human expansion of the greenhouse effect. So this is the warming that happens when the atmosphere traps the heat coming from the Earth that is going towards space. Okay, so to mitigate climate change, the United Nations, specifically the Paris Agreement, set a target of limiting the average warming to around 2 degrees Celsius above pre-industrial temperatures. So this is a very ambitious goal. So to reach this goal, so we need first we need a new technology framework. So we need capacity building framework, and most importantly, we need big funds. So countries around the world actually set objectives to attain what we call the low carbon society. So the basic idea of the low carbon society is to cut down on all the carbon dioxide emissions without endangering development or any developing needs. So actually, the carbon dioxide, the low carbon society can eventually lead to a carbon neutral society. So in the ultimate sense, it can lead to a society that emits greenhouse gases only in the amount that can be absorbed by nature. So this is the definition of a carbon neutral society. So how do we build a low carbon society? So let's take, for example, Japan. So in May 2007, so a long time ago, the Ministry of Environment in Japan, they expressed interest in cutting the global emission by half by 2050. So they enumerated 2 keys on achieving a low carbon society. First is or a carbon neutral society. The first is to build a low carbon society, and the second is to promote innovative technology development. So our project, our JST-NSF funded project, was under the second key, which is promoting innovative technology. So according to their manifesto, so the vision of a low carbon society is divided into 4 philosophies. So there's what they call the principles, images, strategies to realizing low carbon society, and then sharing of experiences and ideas among countries. So under these philosophies, this starts with the person. So it starts from the person, the family, the community, and until the whole world. So our project is under images, under forest and agriculture, and particularly the production of a promising biofuel, which is 1-butanol. So biofuel is considered as an important alternative to petroleum fuels. So since biofuel is made through biological process, it can help attain Okay, so this is our project. So I was lucky enough to be part of this project. This is a US-Japan joint research project. So under the funding of the NSF, the National Science Foundation of the United States, and the JST, or the Japan Science and Technology Agency of Japan. So our research field is under this title, Metabolomics for a Low Carbon Society. And so specifically, we were tasked to produce 1-butanol using microorganisms. So we developed a novel metabolomics analysis system for 1-butanol production. So there were so many people who were involved in this project. So that's the Japan team led by Professor Ichiro Fukusaki of Osaka University. That's me with the black hair. And that is the USA team under NSF, led by Professor James Liao of UCLA. Okay, so this program started with the construction of a 1-butanol producing E. coli strain. So 1-butanol is native in Clostridium. So under anaerobic conditions, so NAD plus is regenerated by the formation of fermentation end products like succinate, lactate, and ethanol. Now, so we introduce a modified Clostridial 1-butanol pathway in E. coli. So this pathway consumes NADH2, the same with the fermentation pathways. So what we did is we delete all these fermentation pathways, and so that 1-butanol pathway will act as the sole electron sink. So hence we were able to produce a 1-butanol producing E. coli strain. So this is under anaerobic condition. So under anaerobic condition growth, it's coupled with 1-butanol production. So, however, this microorganism, or this transgenic E. coli, was beset with several problems. So first, if you look at the obvious strain improvement strategies, the pathway is optimized, and all the obvious competing pathways have been deleted. So second, it only produces 1-butanol in rich medium. So third, the high titer production was already close to the toxicity level of 1-butanol. So that's the third one. And the fourth one, the E. coli production pathway still uses glucose as carbon source. So those are the four problems. So since rational metabolic engineering targets have been exhausted, so we have to come up with an alternative approach to identify new gene targets. So this is where metabolomics comes in. So metabolomics is the comprehensive analysis of metabolites and other small molecules in biological samples. So this is an emerging field in omics research. So for metabolomics, we can use a wide variety of biological samples from plants, animals, cells. We can analyze food, even other chemicals for pharmaceuticals. So for metabolomics, we use various instruments and techniques ranging from chromatography, mass spectrometry, and data analysis tools. So since the metabolome is nearest to the phenotype, so we believe that it can serve as an important determinant for the description of a phenotype or a phenomenon. So of course, nowadays, metabolomics is used with other omics approaches. what we call the multi-omics approach. That's the best way to use omics researches. So here is an experimental, an example of an experimental workflow for metabolomics. So we start with cultivation. So this is in case of bacteria. And then after cultivation, we do sampling. So usually we quench the sample, and then we do fast filtration using filter paper. So after that, we do metabolites extraction using the appropriate solvent. So in our case, we use a mixed solvent, methanol, water, and chloroform. So this is for the extraction of the intracellular metabolites. Now for the case of the extracellular metabolites, so we just centrifuge, we just harvest the cells, and then we collect the supernatant. And then the supernatant will be the one that will be analyzed. So after that, we do extracellular analysis using GCFID for determination of organic acids and alcohols. And then for the intracellular analysis, we use the ion pair LCMS. So after that, we have the data. In the data, we clean them. We make the proper matrix, and then we do multivariate analysis. So that's the experimental workflow for metabolomics. So in the engineered E. coli for one butanol production, so we created two driving forces. So the first one is the NADH driving force. So we created this by deleting the NADH consuming pathways, the succinate, lactate, and ethanol production, and then introduce an NADH producing pathway, which is the formation of formate, the conversion of formate to CO2. And the second one is the creation of an acetyl-CoA driving force. So this one was created by deleting the formation of acetate from acetyl-CoA. So this strategy assumes that all the acetyl-CoA will be funneled to one butanol production. So here, all the obvious gene targets for strain improvement have been exhausted. So when we look at the one butanol production for this strain, we found out that it's still low if you compare it to the production of ethanol or isopropanol in the same organism, E. coli. So what we did is to do comparative metabolomics of the one butanol producing strains. So we have two strains, the low producer and the high producer. The only difference between the two is the PTA deletion. So the PTA is the one that causes the acetyl-CoA driving force. So we did this comparative metabolomics analysis to search for non-obvious gene targets for strain improvement. So when we analyzed the extracellular metabolites, we found out that there was a major decrease in acetate when PTA was deleted. But then there was not a very high increase in one butanol production, meaning the increased carbon flux was not fully used in this strain. So that's why we subjected the intracellular metabolite sample to analysis. So we subjected the intracellular metabolome data to multivariate analysis. So in this case, we did a PCA, or the principal component analysis of the ion pair LCMS and MS data. So if you look at the score plot, we can see that there is a clear separation of the two strains. So the low producer on the left and the high producer on the right. And then if we look at the corresponding loading plot, we can see each dot there, the green dots and the red dots, represent metabolites. So these are the metabolites that contribute to the separation of the two strains. So the farther they are from the middle, the more important they are for the analysis. So I would like to highlight the red ones here. So these are the pyruvate, glutamate, CoA intermediates, and free CoA. So these are the metabolites that are very important for this analysis. So specifically, pyruvate and butanoate were accumulated in the stream in the high producer. But this increase in pyruvate was not used efficiently for 1-butanol production. So there was a problem with the strain. So we found out 3 problems in the strain. So first, the step from butanoyl CoA and butanol was the limiting step. And this one is the one that caused a butanate accumulation. So that's the first one. The second one, there was an entrapment of CoA in the cells as CoA intermediates. So because of this, there is a shortage of CoA, and this causes pyruvate accumulation. So these are the 3 problems that beset this particular strain. So all these observations were not obvious without the metabolomics data. So using this data, we came up with a strategy to optimize the ADH2 expression level. So it's here. Okay, so this part here. So we optimize the enzyme activity of the ADH2 enzyme. And interestingly enough, we found the corresponding increase in 1-butanol production after optimization of the ADH expression level. So, so the metabolome data gave us a clear picture on how to approach the strain improvement strategy for high production of 1-butanol in E. coli. Okay, so in the future, the goal is essentially to reduce the carbon footprint and establish a carbon neutral society. So the next step was for us to embark on a photosynthetic bioproduction system using cyanobacteria. So this is very attractive because it enables the conversion of CO2 to fuels and chemicals. So this has been done by many scientists already using different cyanobacterial species. So the use of cyanobacteria is very attractive because first, they grow relatively faster than plants. And then they will also avoid conflict with food and land. Okay, so we put the same 1-butanol biosynthetic pathway in cyanobacteria. But we found out that it doesn't produce much of 1-butanol. So what we did is to replace some of the steps here. So the first one is to replace the acetyl-CoA driving force with an ATP-driven malonyl-CoA mediated reaction. And then replace the NADH dependent reactions with NADPH dependent reactions. And then lastly, we replace the oxygen sensitive BLDH enzyme with an oxygen tolerant enzyme PDUP. So all these steps resulted in a high 1-butanol production, or a high 1-butanol final titer. Okay. So, but if you compare this with E. coli can produce 30 grams per liter in 7 days. The S. elongatus can only produce 0.3 in 12 days. So, we also did metabolomics analysis of the indigenous cyanobacteria. So, we increased the 1-butanol titer by 74%. So, we do this cycle over and over until we get a very high 1-butanol production. So, the next step for this is to improve to improve the activity of the ACC, ABC enzyme to convert acetyl-CoA directly to malonyl-CoA so that it doesn't go to the TCA cycle. Okay, so I would just like to wrap up the presentation. So for metabolomics, for the use of metabolomics, we can use it for the study of microbiomes to characterize biological pathways and functional roles of microbes. We can investigate the response of microorganisms to various environmental stressors and to discover novel metabolites for innovative applications. And also we can use it for biomarker discovery. So this one, we use metabolomics as a tool to achieve these goals. So, okay. So the future plan is to establish a metabolomics laboratory similar to the one with Dr. DOST-STII, and also to use this for functional genomics and biomarker discovery. So thank you very much.